Alright everybody, so it's been a few days since I was messing around with this grinder, and the last thing I was doing was I was playing around with the size of the capacitor in the auxiliary winding circuit. And I found that as I continued to increase the capacitance, that the grinder would start faster. So I was trying to find that sweet spot where it seemed like the grinder was starting really easily. And then it occurred to me that I might be getting into an area where, sure, it might be starting faster, but I might be losing something on the torque end when it comes up to speed. So in other words, when we start to put a load on the grinder, grinding something, is it going to be able to recover the torque as quickly and compensate for that? So, you know, my situation is that I don't know what the original capacitance was that was in this grinder. I have to make a couple of assumptions. I'm assuming that there were no other capacitors in here, that this was not set up as a capacitor start, capacitor run setup. So I was playing around with the size of the capacitance. We know that what's in here now is a 3.3 microfarad dual section capacitor in parallel, giving me a total effective capacitance of around 6.6 microfarad, and it's actually measuring closer to 5. So with the 5 mic capacitor back in there, it starts slow, but it seems to run okay. Well, I don't know whether or not, I mean, that's what was in there when I bought the thing, but I don't know whether or not that's what was originally called for. I have to make an, if I go with that size, I'm making the assumption that the previous person who was in here and replaced this cap replaced it with a cap that matched what he took out, the original, you know, if that was even the original he took out, who knows. So my conundrum here is, how do I determine? So I tried just adding capacitance. I have, like, for instance, this 6 mic that the original one, I tried running it in there, and then I put in a 22.5, and the thing started a lot better. So then I went, well, if 22.5's good, I went to a 30. And when I went to 30 microfarad, there's virtually no difference. When I went to bridging these two capacitors together in parallel, which gives me effectively about 55 microfarad, again, start time didn't seem to really change. Still seemed to start about the same as it did with the 22.5. But I noticed when it's at speed running, there are different sounds coming from different, there's a certain oscillation that's going on here to the mechanical sound of the grinder that changes, and the speed of that oscillation is changing, for lack of a better term. And then I noticed at some point an odor, and I realized that the odor turned out to be my fresh paint job starting to cook. So I put my hand on the top of the grinder here, and I found that the grinder had gotten very hot, and I don't know at what point that had started to happen. And the cast iron body of this motor and the base, it holds the heat so well that long after I shut it down, the heat was retained. So I figured, well, I'm going to have to wait until it just cools off completely and try and figure out what was going on here. I decided what I'm going to do is I'm going to try and determine where the grinder is, for lack of a better term, happiest operating. And I have a few things I can do. I have an infrared thermometer, okay? So I can actually measure the temperature of the case before it runs, and then I can measure the temperature of the case after it's run for a few minutes and see how much of a temperature rise we're getting. As long as I make sure I measure at the same spot each time, I should be good to go. So I turn the grinder around sideways on the bench here for a couple of reasons. I can get to the back where it's easiest to get that measurement with the temperature gauge. And also, the reason why I turned it on its side here is so that I have this shaft on the side here, because the other thing I want to look at is I want to look at max speed with the tachometer, because I think that from the sound change, the mechanical oscillation, I think might be actually a variation in the max RPMs. Now, unloaded with just this wheel on here, once it comes up to speed, I would think the point where it's at max RPM might be what we're shooting for. In other words, what I'm trying to do is I'm trying to determine what size capacitance gives me a 90-degree phase relationship between these two windings. If I don't have the optimum phase relationship between the two windings, the two magnetic fields almost start to fight with each other, for lack of a better term, and start to kind of cancel each other out. But this struggle that they have comes at a cost. I would expect the RPMs to be lower because one winding is almost acting like a brake on the other winding. And also, that extra energy that's being not turned into rotating motion has got to turn into something else. And in this case, I think it's turning into the heat. So I think when I had my phasers, when I put the largest capacitance on there, when I got up to like 50 microfarad, I think at that point my phase relationship was so screwy that I think the magnetic fields were really having a hard time with each other and converting that into heat. I also would have expected at that point that my amperage draw had gone up, which I wasn't monitoring. So the three parameters I'm going to monitor temperature of the case. Really, it's a delta T that we're looking at. What's the start temperature? After it runs for so many minutes, what's it end up at? Second thing I'm going to monitor is what is my current draw once it comes up to speed. And the third thing is I'm going to monitor what is my max RPM once it's up to speed. And we'll try a few different size capacitors, and we'll see how it looks. So I'm going to use a 2-minute timer on my phone to decide when I'm going to take the second temperature measurement. So I'm going to start with the original cap, so we get about 6.5, 7 microfarad there. And I think I'm going to take a little piece of tape, blue painter's tape, and give myself a little target on the back of the body of the grinder, so I'm getting a measurement in the same spot each time. So we get a start temperature of 64 degrees Fahrenheit, and I think we're ready for our first run. So 1.82 amps. .3600 RPM. It's right on the verge of 67 degrees. All right, I'm going to wait for it to spin down and put in the 22.5 microfarad cap. I'm going to try the 30 microfarad cap, which is a slight increase over this one, but I think I see which way this is going. So it's been about 15 minutes, and it's still at 75 degrees, so you can see how that cast iron really tends to still hold that heat. So now I've got the 30 mic on. The bump up. You can hear that oscillation a lot more. 83 degrees. So I've developed a recurring theme here, which is that the increase in microfarads causes a decrease in RPM, an increase in current draw, and an increase in temperature. It seems like where I started with this original cap seems to be best, but I want to try one more thing. I'm not going to try the 30 and the 22 put together, which would be 52, because I think that's probably what really started cooking that housing on me. I'm actually, now that it's been sitting for a while, I can actually feel latent heat on the top here. Yeah, it's now sitting there at 86 degrees, so it's actually risen 3 more degrees just sitting here doing nothing. So what I'm going to do now is I separated the 2 wires on the capacitor that were hooked together, which were effectively putting these 2 capacitors in parallel. And what that's going to allow me to do is that's going to allow me to try and use just one section of the cap, which is going to effectively give me about 3.3 microfarads. So this is going to be the lowest capacitance yet. Let's see what this does. I suspect it's going to be really slow to start. So I venture to guess that the 2 sections of this cap aren't measuring the same exact capacitance any longer, so just for the heck of it, I'm going to try the other section. Now, just for the heck of it, with the bearings warmed up, I'm going to bridge the 2 capacitors in parallel again, go back to my first test, because I just want to see what the temperature rise is going to be, because those last 2 tests only had a 1 degree temperature change, but they were going from like 86 to 87, then 87 to 88, whereas when I started the test, the thing was completely cold. I was going from 64 and it went to 67, which is a 3 degree temperature raise. I'm curious to see what happens. All right, let's review the results of my tests here. Okay, first test with the original capacitor that was in here when I got the machine, which we assume is about a 6 microfarad. The amp draw is 1.82 amps. Start temperature was 64, end temperature was 67, so we had a delta T, change in temperature or rise in temperature of 3 degrees. The RPMs was 3,600 RPMs. It's probably what the motor's rated for. When we bumped up the capacitance to 22.5 microfarad, effectively more than tripling it, almost quadrupling it, we ended up having a large increase in the amp draw. It went to 4.8 amps, and we had a big temperature increase. Delta T went up to 6 degrees, and we had an RPM drop. So that looks like that's not a good idea. And it appeared that as we continued to increase the capacitance, when I went from 22.5 to 30, which is 5 times the original capacitance, our amp draw went up to 7.6 amps, and we had a delta T of 8 degrees, and the RPMs dropped even further to 3525. So all indications are that we're going in the wrong direction here, that this original capacitance is much closer to what should be in here. Just for the heck of it, we tried dropping the capacitance down from 6 microfarad to about half, somewhere around 3.3. We're not positive what those will measure out at, but just for the heck of it, we tried each section in case the 2 sections had, from age, changed capacitance a little bit. Results for both of these tests were almost the same. Amp draw, 2.6 amps, over half an amp increase over the 6, so the amperage went up a little bit here. RPMs still stayed at 3,600. They look pretty good. The temperature, the delta T, actually went down only one degree. I tried that with both sections, got the same result, 1 degree. So I went back to my original test at the top here, and now, because we're going from a warmer start temperature, the delta T dropped 1 degree, from 3 degrees to 2 degrees. Now, my infrared thermometer does not have a it does not have a high resolution. It doesn't have a decimal. So it could be like I could be on the verge of, for instance, when this was reading 88, it could have been like 88.1, or it could have been 88.8. So there's a little bit of error in there. So I think that since this test number 1 and these last 3 tests, the delta T is very, very close on all of these. And because the amperage on the first and the last test are very close, notice that the first time we tried it from a cold start, the amperage was 1.82. From a warm start, it's 1.91. It went up a little bit. Let's see, but that's such a small amount. I'm not too concerned about that. I don't like that it jumped up to 2.6 when I reduced the capacitance. So reducing the capacitance caused a raise in current, and increasing the capacitance caused a raise in current. So we're right in this area here. The only thing I wish I had was, I wish I had a 10 microfarad cap. I'd like to see what a 10 would do, because at some point there's a point where that current would continue to probably go down, maybe. I don't know. The other thing that occurred to me is I should see if I can get any information off this data plate that's on the motor. In other words, we might be able to get some information off of here that might help us figure out where we should be. All right, so I used a magnifying glass and some stronger light, and I was able to just make out some of the data that's on this data plate. It says up here, Hammond Machine Builders, Kalamazoo, Michigan. And then there are various places on the data plate here to be stamped, and this is what I ended up figuring out. So what's in a box is what's actually stamped onto the plate. So the first box says current, which you might think means amps, but apparently they're just using that to denote the type of current, and in this case it's AC. So they must have made some DC versions of these grinders, which really would be early if you're on a if you're on a distribution grid that had DC power. Type appears to be blank. It doesn't look like they ever put anything in that box. Model is 6. So this is a Hammond Model 6 grinder. I think I had figured that out a while back. Horsepower is 1/2. RPM 3450. And I'm actually measuring higher, but I'll get to that in a moment. Amp 5, okay, so 5 amps. So that seems kind of high, or at least what I'm getting right now is kind of low. But then again, I don't know what they're saying here. Are they saying while it's working, while it's grinding, it's 5 amps, or more than likely the problem is down here. Voltage, it says 110. All right, so this is a really early motor, and years ago the standard that was commonly found in a lot of areas would be only 110 volts. I've got good power here on my distribution grid, so I'm getting anywhere in the neighborhood from 120 to 124 volts at any given time. So what's happening, I believe, is because I'm feeding higher voltage into it, a little bit higher than what this is spec'd for, that's going to cause this current to drop. So it's not unusual for this current to go down if you feed it more voltage. It sounds counterintuitive, but that's just with electric motors, that's been my experience. I'm thinking that this would be a little bit lower, because I'm thinking if I actually put this on a variac, for instance, and I drop the voltage down to 110 volts, I bet you that current draw would go up. Maybe not to 5, but it would go up. Also, I'm wondering whether or not that's why my RPMs seem high. 3450 is what it's rated for, but again, that's at 110 volts. If I drop this down to 110 volts, it probably will slow down. And last here is CYC, which stands for cycles. Again, years ago they often did it that way. More commonly now you will see HZ for hertz. 60, which is standard here in the US. PH stands for phase, 1 means that this is a single phase motor. So the most important thing here is that 5 amps draw is what we should expect at 110 volts. So I think I'm going to probably go with that. Well, actually, I did want to check one more thing. I think I might have a 10 microfarad cap laying around here. All right, so I measured the capacitance of that capacitor I have right now, and each section's measuring 4 microfarad. So in parallel, it's a total of 8 microfarad. And I decided I'm going to boost that up just a little bit. I'm going to go with a 10 microfarad. So here on eBay, I found this Dayton, which is a name brand, run capacitor. And it's a 10 microfarad. And it's rated for 440 volts AC. So it should be plenty stout enough for my purposes here. The only thing I have to worry about is is it going to fit. Let's see if they give me dimensions here, but I mean that thing's a moose, so if that fits in there, I'm pretty sure this will. Yeah, actually, it says right here that this thing is it's only 1 9/16 inch in diameter and 2 3/4 inches in height, so I should be able to make that work. Probably just gonna have to make a bracket for it, and that's $10.75 with free shipping.